Headshot.
Hello everyone and welcome to the CEC and AMI guys. So in the strength of material, so today we will learn about the types of strain. In this video series we will cover all the topics of the engineering, mechanical engineering, and we will try to cover up all the things in the 5 to 10 minutes per topic. So it's like a quick revision. So let's start with the types of a strain. So the types of a strain can be divided into the two parts. The first one is the normal strain, and the second one is the shear strain. Normal strain and the shear strain. The shear strain which is given by the gamma. The normal strain can be further divided into the three parts: longitudinal strain, lateral strain, and the third one is the volumetric strain. And lateral strain can be termed as the transverse strain also. Okay, so all of the three types of the strain can further divided into the two parts. The one is the tensile strain and second one is the compressive strain. Now let's understand what is the difference between the normal strain and longitudinal strain. So the normal strain is given by the change in dimension to the original dimension. Change in dimension to the original dimension. And the longitudinal strain is given by the change in dimension along its length. So longitudinal dimension, the normal strain in the direction of the applied load. Just take an example. Here is the circular bar, and we are pulling the bar with the help of the axial load of the P. So changes in the length, its length is L. Due to the axial load, change in length is del. So the longitudinal strain is given by the change in length to the original length. Next one is the volumetric strain. Volumetric strain, it is the normal strain in the perpendicular. Volumetric strain is given by the change in the total volume. So volumetric strain is given by the change in volume to the original volume, which is the summation of strain in x direction, y direction, and the summation of z direction. So if we are here taking then a rectangular block, if we are taking the rectangular block, it is the length, width, and thickness of the block. So the volume will be the L B into T. So the volumetric strain for the rectangular block is given by the del V by V is equals to del L upon L, change in longitudinal dimension, plus del B by B, change in width, and del T by T, change in lateral dimension. Now taking then a cylindrical bar. Now taking the example of the cylindrical bar, as we know that the volume of the cylinder is equals to pi by 4 d square L. So the change in volume to the original volume is the volumetric strain of the cylindrical bar, which is given by the longitudinal strain plus 2 times of the lateral strain. very important formula. Directly you will use the you will find the application in the get numerical problem. So directly mug up all of this formula. Now we are taking the example of the cylindrical pressure vessel. Cylindrical pressure vessel. So in case of the cylindrical pressure vessel, the longitudinal strain is given by the del L upon L, and the del D by D is called the hoop strain. So the volumetric strain is given by the del V by V is equals to longitudinal strain plus 2 times of the hoop strain. Now taking the spherical body. Now taking the spherical body or spherical object, what will be the volume? So volume of the sphere is given by the 4 by 3 pi r cube. 4 by 3 pi r cube is equals to, change in volume is given by the pi by 6 3d square del d. So from here we can say that the volumetric strain in case of the spherical body is given by the del V by V, which is equals to 3 times of the hoop strain. 3 times of the hoop strain. So we have considered all of the 3 cases, the cylindrical, sphere and the rectangular block. Now the expression for the Now we are moving to the strain, volumetric strain in case of a triaxial loading. In case of a triaxial loading, volumetric strain, as we discussed above, is given by the del V by V is equals to del L upon N plus del B upon B plus del T upon T, which is equals to strain in x direction plus strain in y direction plus strain in z direction. So in the general case, the strain can be calculated by the, if the stress are given in the x, y and the z direction, then how to find the strain in the x, y and z direction, which is given by the epsilon x is equals to del L upon L is equals to 1 by E. For the x, here take sigma x minus mu times of the sigma y plus sigma z. The strain in the y direction is given by the del B upon B is equals to 1 by E stresses in the y direction minus mu into stresses in x direction plus stresses in the z direction. For the strain in the z direction is given by the del T upon T, which is equals to 1 by E of the stresses in the z direction minus mu times of the sigma y plus sigma x. So by all combining all of the 3 strain, we can calculate the volumetric strain. So on combining all of this, we can generalize one formula which is given by this. When you put all of the value in the volumetric strain, you will find the expression volumetric strain del V by V is equals to 1 minus 2 mu by E into sigma x plus sigma y plus sigma z. So for the volumetric strain, in case when the stresses in the x, y and z direction are given, you can use directly this formula. Now considering the one case when the mu is equals to 0.5, that is the case of the perfect plastic. That is the case of the perfect plastic. In case of the mu is given is 0.5, or in the question it is written that the perfect plastic, So mu will be the 0.5, and we will put this value. You will find that the stresses in the x direction plus y direction plus z direction is equals to 0, because as you can see that when you will put the mu value 0.5, it terms will with 0, then always its summation will always 0. So it is the condition for the perfect plastic body. Now moving to the shear strain. The normal strain, we are considered all of the cases. Now we are moving to the shear strain. The shear strain is given by the gamma is equals to del by L. So it is the only one formula which can be directly used to find the shear stresses. Okay. Now we are considering some of the important direct values which are asked in the question. So for the material and independent elastic constant. Elastic constant are used to determine the strain theoretically. To find the strain theoretically, we will use the elastic constant for the material which is the isotropic. The material which is isotropic, the independent elastic constant are required is the 2. For the orthotropic material, the independent elastic constant are required is equals to 9, and for the anisotropic material, the constant are required, independent elastic constant are required is the 21. These are the standard value which are asked in the question directly. Now we are taking the relation for the stress and strain, elastic constant, Young modulus of elasticity, the modulus of rigidity, and the mu. So these are the 3 important formula which are the very important to find the relation, and if the NR2 value are given, so you have to be put the value in that formula, and you can find the value of the other one. So this relation and the relation for the elastic constant are given by the relationship for the elastic constant. The first one is the E equals to 2k 1 plus mu. The second one is the E equals to, this is the E equals to 2g. E equals to 2g 1 plus mu. E equals to 3k 1 minus 2 mu, and the third one is the E equals to 9 kg divided by 3k plus g. So these are the relationship for the elastic constant. So you can see that here the constant term is the 2, then the 3, then the 9. So there is one trick you can learn easily all of this formula. When you will write the alphabet, you will find that the G will come first, so it will comes with the 2, and the K will comes after the G, that means it will comes with the 3. So this is the just a common trick. You can learn all of this formula by this. So thank you guys, and for the more video update, subscribe our channel. Thank you.